in a wide varied engine at almost right angles to the engine axis. Therefore, in order to give a positive flow, the air must surround the engine compressor at a positive pressure before entering the compressor. Included in some installations as necessary parts of the plenum chamber are the auxiliary air intake doors, blow-in doors. These blow-in doors admit air to the engine compartment during ground operation. When air requirements for the engine are in excess of the airflow through the inlet ducts, the doors are held closed by spring action. When the engine is not operating, during operation, however, the doors open automatically whenever engine compartment pressure drops below atmospheric pressure. During takeoff and flight, ram air pressure in the engine compartment aids the springs in holding the doors closed. The diffuser is an annular chamber provided with a number of vanes forming a series of divergent passages into the manifold. The diffuser vanes direct the flow of air from the impeller to the manifold at an angle designed to retain the maximum amount of energy imparted by the impeller. They also deliver the air to the manifold at a velocity and pressure satisfactory for use in the combustion chambers. Refer to Figure 1-46A and note the arrow indicating the path of airflow through the diffuser, then through the manifold. The compressor manifold shown in Figure 1-46A diverts the flow of air from the diffuser, which is an integral part of the manifold, into the combustion chambers. The manifold has one outlet port for each chamber so that the air is evenly divided. A compressor outlet elbow is bolted to each of the outlet ports. These air outlets are constructed in the form of ducts, and are known by a variety of names, such as air outlet ducts, outlet elbows, or combustion chamber inlet ducts, regardless of the terminology used. These outlet ducts perform a very important part of the diffusion process. That is, they change the radial direction of the airflow to an axial direction, in which the diffusion process is completed after the turn. To help the elbows perform this function in an efficient manner, turning vanes, cascade vanes, are sometimes fitted inside the elbows. These vanes reduce air pressure losses by presenting a smooth, turning surface. Figure 1-46B, Axial Flow Compressor. The axial flow compressor has two main elements, a rotor and a stator. The rotor has blades fixed on a spindle. These blades impel air rearward in the same manner as a propeller because of their angle and airfoil contour. The rotor, turning at high speed, takes in air at the compressor inlet, and impels it through a series of stages, from inlet to exit. The air flows along an axial path, and is compressed at a ratio of approximately 1.25, 1 per stage. The action of the rotor increases the compression of the air at each stage and accelerates it rearward through several stages. With this increased velocity, energy is transferred from the compressor to the air in the form of velocity energy. The stator blades act as diffusers at each stage, partially converting high velocity to pressure. Each consecutive pair of rotor and stator blades constitutes a pressure stage. The number of rows of blades, stages, is determined by the amount of air and total pressure rise required. Compressor pressure ratio increases with the number of compression stages. Most engines utilize up to 16 stages and more. The stator has rows of vanes, which are in turn attached inside an enclosing case. The stator vanes, which are stationary, project radially toward the rotor axis, and fit closely on either side of each stage of the rotor blades. In some cases, the compressor case, into which the stator vanes are fitted, is horizontally divided into halves. Either the upper or lower half may be removed for inspection or maintenance of rotor and stator blades. The function of the stator vanes is to receive air from the air inlet duct, or from each preceding stage, and increase the pressure of the air, and deliver it to the next stage at the correct velocity and pressure. They also control the direction of air to each rotor stage, to obtain the maximum possible compressor blade efficiency. Shown in Figure 1-48 are the rotor and stator elements of a typical axial flow compressor. The first stage rotor blades can be preceded by an inlet guide vane assembly that can be fixed or variable. The guide vanes direct the airflow into the first stage rotor blades at the proper angle, and impart a swirling motion to the air entering the compressor. This press swirl, in the direction of engine rotation, improves the aerodynamic characteristics of the compressor by reducing drag on the first stage rotor blades. The inlet guide vanes are curved steel vanes usually welded to steel inner and outer shrouds. At the discharge end of the compressor, the stator vanes are constructed to straighten the airflow to eliminate turbulence. These vanes are called straightening vanes or the outlet vane assembly. The casings of axial flow compressors not only support the stator vanes, and provide the outer wall of the axial path the air follows, but they also provide the means for extracting compressor air for various purposes. The stator vanes are usually made of steel with corrosion and erosion-resistant qualities. Quite frequently, they are shrouded, enclosed, by a band of suitable material. To simplify the fastening problem, the vanes are welded into the shrouds, and the outer shroud is secured to the compressor housing inner wall by radial retaining screws. The rotor blades are usually made of stainless steel with the latter stages being made of titanium. The design of 1-41. Front compressor stator casing. Rear compressor stator casing. Compressor rotor compressor rear frame. Rear compressor stator casing. Front compressor stator casing. Figure 1-48. Rotor and stator elements of a typical axial flow compressor. Blade attachment to the rotor disc rims varies, but they are commonly fitted into discs by either bolt type or fir tree methods. Figure 1-49. The blades are then locked into place by differing methods. Compressor blade tips are reduced in thickness by cutouts, referred to as blade profiles. These profiles prevent serious damage to the blade or housing should the blades contact the compressor housing. This condition can occur if rotor blades become excessively loose, or if rotor support is reduced by a malfunctioning bearing. Even though blade profiles greatly reduce such possibilities, occasionally a blade may break under stress of rubbing, and cause considerable damage to compressor blades and stator vane assemblies. The blades vary in length from entry to discharge because the annular working space, drum to casing, is reduced progressively toward the rear by the decrease in the casing diameter. Figure 1-50. This feature provides for a fairly constant velocity through the compressor, which helps to keep the flow of air constant. The rotor features either drum-type or disc-type construction. The drum-type rotor consists of rings that are flanged to fit one against the other, wherein the entire assembly can then be held together by through bolts. This type of construction is satisfactory for low-speed compressors where centrifugal stresses are low. The disc-type rotor consists of a series of discs machined from aluminum forgings, shrunk over a steel shaft, with rotor blades dovetailed into the disc rims. Another method of rotor construction is to machine the discs and shaft from a single aluminum forging, and then to bolt steel stub shafts on the front and rear of the assembly to provide bearing support surfaces and splins for joining the turbine shaft. The drum-type and disc-type rotors are illustrated in figures 1-50 and 1-51, respectively. Bolt root fit tree root. Figure 1-49. Common designs of compressor blade attachment to the rotor disc. 1-42. Airflow. Figure 1-50. Drum-type compressor rotor. Rotor blade, stator blade. Figure 1-51. Disc-type compressor rotor. The combination of the compressor stages and turbine stages on a common shaft is an engine referred to as an engine spool. The common shaft is provided by joining the turbine and compressor shafts by a suitable method. The engine spool is supported by bearings, which are seated in suitable bearing housings. As mentioned earlier, there are two configurations of the axial compressor currently in use, the single rotor/spool, and the dual rotor/spool, sometimes referred to as solid spool and split spool, two-spool, dual spool. One version of the solid spool, one-spool, compressor uses variable inlet guide vanes. Also, the first few rows of stator vanes are variable. The main difference between variable inlet guide vane, VIF, and a variable stator vane, VSV, is their position with regard to the rotor blades. VIF are in front of the rotor blades, and VSV are behind the rotor blades. The angles of the inlet guide vanes and the first several stages of the stator vanes can be variable. During operation, air enters the front of the engine and is directed into the compressor at the proper angle by the variable inlet guide and directed by the VSV. The air is compressed and forced into the combustion section. A fuel nozzle that extends into each combustion liner atomizes the fuel for combustion. These variables are controlled in direct relation to the amount of power the engine is required to produce by the power lever position. Most turbofan engines are of the split spool compressor type. Most large turbofan engines use a large fan with a few stages of compression called the low-pressure spool. These turbofans incorporate two compressors with their respective turbines and interconnecting shafts, which form two physically independent rotor systems. Many dual rotor systems have rotors turning in opposite directions, and with no mechanical connection to each other. The second spool, referred to as the high-pressure spool, and is the compressor for the gas generator and core of the engine, supplies air to the combustion section of the engine. The advantages and disadvantages of both types of compressors are included in the following list. Even though each type has advantages and disadvantages, each has its use by type and size of engine. The centrifugal flow compressor's advantages are high pressure rise per stage, efficiency over wide rotational speed range, simplicity of manufacture and low cost, low weight, and low starting power requirements. The centrifugal flow compressor's disadvantages are its large frontal area for a given airflow and losses in turns between stages. The axial flow compressor's advantages are high peak efficiencies, small frontal area for given airflow, straight-through flow, allowing high ram efficiency, and increased pressure rise by increasing number of stages, with negligible losses. 1-43. The axial flow compressor's disadvantages are good efficiencies over only narrow rotational speed range, difficulty of manufacture and high cost, relatively high weight, and high starting power requirements, partially overcome by split compressors. Diffuser. The diffuser is the divergent section of the engine after the compressor, and before the combustion section. It has the all-important function of reducing high-velocity compressor discharge air to increased pressure at a slower velocity. This prepares the air for entry into the flame-burning area of the combustion section at a lower velocity, so that the flame of combustion can burn continuously. If the air passed through the flame area at a high velocity, it could extinguish the flame. Combustion section. The combustion section houses the combustion process, which raises the temperature of the air passing through the engine. This process releases energy contained in the air/fuel mixture. The major part of this energy is required at the turbine or turbine stages to drive the compressor. About squared/cubed of the energy is used to drive the gas generator compressor. The remaining energy passes through the remaining turbine stages that absorb more of the energy to drive the fan, output shaft, or propeller. Only the pure turbojet allows the air to create all the thrust or propulsion by exiting the rear of the engine in the form of a high-velocity jet. These other engine types have some jet velocity out the rear of the engine, but most of the thrust or power is generated by the additional turbine stages driving a large fan, propeller, or helicopter rotor blades. The primary function of the combustion section is, of course, to burn the fuel/air mixture, thereby adding heat energy to the air. To do this efficiently, the combustion chamber must provide the means for proper mixing of the fuel and air to assure good combustion. Burn this mixture efficiently. Cool the hot combustion products to a temperature that the turbine inlet guide vanes/blades can withstand under operating conditions, and deliver the hot gases to the turbine section. The location of the combustion section is directly between the compressor and the turbine sections. The combustion chambers are always arranged coaxially with the compressor and turbine regardless of type, since the chambers must be in a through-flow position to function efficiently. All combustion chambers contain the same basic elements. 1. Casing. 2. Perforated inner liner. 3. Fuel injection system. 4. Some means for initial ignition. 5. Fuel drainage system to drain off unburned fuel after engine shutdown. There are currently 3 basic types of combustion chambers, variations within type being in detail only. These types are 1. Can type. 2. Can annular type. 3. Annular type. The can type combustion chamber is typical of the type used on turboshaft and apis. Figure 1-52. Each of the can type combustion chambers consists of an outer case or housing, within which there is a perforated stainless steel, highly heat resistant combustion chamber liner or inner liner. Figure 1-53. The outer case is removed to facilitate liner replacement. Figure 1-52. Can type combustion chamber. Older engines with several combustion cans had each can with interconnector, flame propagation tube, which was a necessary part of the can type combustion chambers. Since each can is a separate burner operating independently of the other cans, there must be some way to spread combustion during the initial starting operation. This is accomplished by interconnecting all the chambers. As the flame is started by the spark igniter plugs in 2 of the lower chambers, it passes through the tubes and ignites the combustible mixture. 1-44. Figure 1-53. Inside view of a combustion chamber liner, in the adjacent chamber, and continues until all the chambers are burning. The flame tubes vary in construction details from one engine to another, although the basic components are almost identical. Figure 1-54. The spark igniters previously mentioned are normally 2 in number, and are located in 2 of the can-type combustion chambers. Another very important requirement in the construction of combustion chambers is providing the means for draining unburned fuel. This drainage prevents gum deposits in the fuel manifold, nozzles, and combustion chambers. These deposits are caused by the residue left when the fuel evaporates. Probably most important is the danger of afterfire, if the fuel is allowed to accumulate after shutdown. If the fuel is not drained, a great possibility exists that, at the next starting attempt, the excess fuel in the combustion chamber will ignite and exhaust gas temperature will exceed safe operating limits. The liners of the can-type combustors have perforations of various sizes and shapes, each hole having a specific purpose and effect on flame propagation within the liner. Figure 1-52. The air entering the combustion chamber is divided by the proper holes, louvers, and slots into 2 main streams, primary and secondary air. The primary or combustion air is directed inside the liner at the front end, where it mixes with the fuel and is burned. Secondary or cooling air passes between the outer casing and the liner and joins the combustion gases through larger holes toward the rear of the liner, cooling the combustion gases from about 3,500 degrees Fahrenheit to near 1,500 degrees Fahrenheit. To aid in atomization of the fuel, holes are provided around the fuel nozzle in the dome or inlet end of the can-type combustor liner. Louvers are also provided along the axial length of the liners, to direct a cooling layer of air along the inside wall of the liner. This layer of air also tends to control the flame pattern by keeping it centered in the liner, thereby preventing burning of the liner walls. Figure 1-55 illustrates the flow of air through the louvers in the annular combustion chamber. Some provision is always made in the combustion chamber case for installation of a fuel nozzle. The fuel nozzle delivers the fuel into the liner in a finely atomized spray. The more the spray is atomized, the more rapid and efficient the burning process is. 2 types of fuel nozzle currently being used in the various types of combustion chambers are the simplex nozzle and the duplex nozzle. The construction features of these nozzles are covered in greater detail in Chapter 3, Engine Fuel and Fuel Metering Systems. Interconnector tube elbow seal Ferrule seal elbow extension tube, Figure 1-54. Interconnecting flame tubes for can-type combustion chambers. 1-45. Outlet ducts, flame tubes, rotor shaft, Figure 1-55. Annular combustion chamber liner. The spark igniter plugs of the annular combustion chamber are the same basic type used in the can-type combustion chambers. Although construction details may vary, there are usually 2 igniters mounted on the bus provided on each of the chamber housings. The igniters must be long enough to protrude from the housing into the combustion chamber. The burners are interconnected by projecting flame tubes, which facilitate the engine starting process as mentioned previously in the can-type combustion chamber familiarization. The flame tubes function identically to those previously discussed, differing only in construction details. This type of combustion chamber is not used in modern engines. The forward face of each chamber presents 6 apertures, which align with the 6 fuel nozzles of the corresponding fuel nozzle cluster. Figure 1-56. These nozzles are the dual orifice, duplex, type requiring the use of a flow divider. Pressurizing valve. As mentioned in the can-type combustion chamber discussion, around each nozzle are press swirl vanes for imparting a swirling motion to the fuel spray, which results in better atomization of the fuel, better burning, and efficiency. The swirl vanes function to provide 2 effects imperative to proper flame propagation. 1. High flame speed. Better mixing of air and fuel, ensuring spontaneous burning. 2. Low air velocity axially. Swirling eliminates overly rapid flame movement axially. The swirl vanes greatly aid flame propagation. Since a high degree of turbulence in the early combustion and cooling stages is desirable, the vigorous mechanical mixing of the fuel vapor with the primary air is necessary. Since mixing by diffusion alone is too slow, this same mechanical mixing is also established by other means, such as placing coarse screens in the diffuser outlet, as is the case in most agile flow engines. Fuel nozzle cluster spark igniter. Figure 1-56. Can-annular combustion chamber components and arrangement. The can-annular combustion chambers also must have the required fuel drain valves located in 2 or more of the bottom chambers, assuring proper drainage and elimination of residual fuel burning at the next start. The flow of air through the holes and louvers of the can-annular chambers is almost identical with the flow through other types of burners. Figure 1-56. Special baffling is used to swirl the combustion airflow and to give it turbulence. Figure 1-57 shows the flow of combustion air, metal cooling air, and the diluent or gas cooling air. The airflow direction is indicated by the arrows. Combustion air, metal cooling air, gas cooling air. Figure 1-57. Airflow through a can-annular combustion chamber. The basic components of an annular combustion chamber are a housing and a liner, as in the can type. The liner, 1-46, consists of an undivided circular shroud extending all the way around the outside of the turbine shaft housing. The chamber may be constructed of heat-resistant materials, which are sometimes coated with thermal barrier materials, such as ceramic materials. The annular combustion chamber is illustrated in Figure 1-58. Modern turbine engines usually have an annular combustion chamber, as can be seen in Figure 1-59. The annular combustion chamber also uses louvers and holes to prevent the flame from contacting the side of the combustion chamber. Figure 1-58. Annular combustion with chamber ceramic coating. Figure 1-59. Combustion chamber louvers and holes. Turbine section. The turbine transforms a portion of the kinetic velocity energy of the exhaust gases into mechanical energy to drive the gas generator, compressor, and accessories. The sole purpose of the gas generator turbine is to absorb approximately 60 to 70% of the total pressure energy from the exhaust gases. The exact amount of energy absorption at the turbine is determined by the load the turbine is driving, that is, compressor size and type, number of accessories, and the load applied by the other turbine stages. These turbine stages can be used to drive a low-pressure compressor, fan, propeller, and shaft. The turbine section of a gas turbine engine is located aft, or downstream, of the combustion chamber. Specifically, it is directly behind the combustion chamber outlet. The turbine assembly consists of 2 basic elements, turbine inlet guide vanes and turbine blades. Figures 1-60 and 1-61. The stator element is known by a variety of names, of which turbine inlet nozzle vanes, turbine inlet guide vanes, and nozzle diaphragm are 3 of the most commonly used. The turbine inlet nozzle vanes are located directly aft of the combustion chambers, and immediately forward of the turbine wheel. This is the highest or hottest temperature that comes in contact with metal components in the engine. The turbine inlet temperature must be controlled or damage will occur to the turbine inlet vanes. Figure 1-60. Turbine inlet guide vanes. Figure 1-61. Turbine blades. After the combustion chamber has introduced the heat energy into the mass airflow and delivered it evenly to the turbine inlet nozzles, the nozzles must prepare the mass airflow to drive the turbine rotor. The stationary vanes of the turbine. 1-47. Inlet nozzles are contoured and set at such an angle that they form a number of small nozzles discharging gas at extremely high speed. Thus, the nozzle converts a varying portion of the heat and pressure energy to velocity energy that can then be converted to mechanical energy through the turbine blades. The second purpose of the turbine inlet nozzle is to deflect the gases to a specific angle in the direction of turbine wheel rotation. Since the gas flow from the nozzle must enter the turbine blade passageway while it is still rotating, it is essential to aim the gas in the general direction of turbine rotation. The turbine inlet nozzle assembly consists of an inner shroud and an outer shroud between which the nozzle vanes are fixed. The number and size of inlet vanes employed vary with different types and sizes of engines. Figure 1-62 illustrates typical turbine inlet nozzles featuring loose and welded vanes. The vanes of the turbine inlet nozzle may be assembled between the outer and inner shrouds or rings in a variety of ways. Although the actual elements may vary slightly in configuration and construction features, there is one characteristic peculiar to all turbine inlet nozzles: the nozzle vanes must be constructed to allow thermal expansion. Otherwise, there would be severe distortion or warping of the metal components because of rapid temperature changes. The thermal expansion of turbine nozzles is accomplished by one of several methods. One method necessitates loose assembly of the supporting inner and outer vane shrouds. Figure 1-62A. A. Turbine nozzle vane assembly with loose-fitting vanes. B. Turbine nozzle vane assembly with welded vanes. Figure 1-62. Typical turbine nozzle vane assemblies. Each vane fits into a contour slot in the shrouds, which conforms to the airfoil shape of the vane. These slots are slightly larger than the vanes to give a loose fit, for further support. The inner and outer shrouds are encased by inner and outer support rings, which provide increased strength and rigidity. These support rings also facilitate removal of the nozzle vanes as a unit. Without the rings, the vanes could fall out as the shrouds were removed. Another method of thermal expansion construction is to fit the vanes into inner and outer shrouds. However, in this method the vanes are welded or riveted into position. Figure 1-62B. Some means must be provided to allow thermal expansion. Therefore, either the inner or the outer shroud ring is cut into segments. The saw cuts separating the segments allow sufficient expansion to prevent stress and warping of the vanes. The rotor element of the turbine section consists essentially of a shaft and a wheel. Figure 1-63. The turbine wheel is a dynamically balanced unit consisting of blades attached to a rotating disc. The disc, in turn, is attached to the main power transmitting shaft of the engine. The exhaust gases leaving the turbine inlet nozzle vanes act on the blades of the turbine wheel, causing the assembly to rotate at a very high rate of speed. The high rotational speed imposes severe centrifugal loads on the turbine wheel, and at the same time the elevated temperatures result in a lowering of the strength of the material. Consequently, the engine speed and temperature must be controlled to keep turbine operation within safe limits. Figure 1-63. Rotor elements of the turbine assembly. The turbine disc is referred to as such without blades. When the turbine blades are installed, the disc then becomes the turbine wheel. The disc acts as an anchoring component for 1-48. The turbine blades. Since the disc is bolted or welded to the shaft, the blades can transmit to the rotor shaft the energy they extract from the exhaust gases. The disc rim is exposed to the hot gases passing through the blades and absorbs considerable heat from these gases. In addition, the rim also absorbs heat from the turbine blades by conduction. Hence, disc rim temperatures are normally high and well above the temperatures of the more remote inner portion of the disc. As a result of these temperature gradients, thermal stresses are added to the rotational stresses. There are various methods to relieve, at least partially, the aforementioned stresses. One such method is to bleed cooling air back onto the face of the disc. Another method of relieving the thermal stresses of the disc is incidental to blade installation. A series of grooves or notches, conforming to the blade root design, are broached in the rim of the disc. These grooves allow attachment of the turbine blades to the disc. At the same time, space is provided by the notches for thermal expansion of the disc. Sufficient clearance exists between the blade root and the notch to permit movement of the turbine blade when the disc is cold. During engine operation, expansion of the disc decreases the clearance. This causes the blade root to fit tightly in the disc rim. The turbine shaft is usually fabricated from alloy steel. Figure 1-63. It must be capable of absorbing the high torque loads that are exerted on it. The methods of connecting the shaft to the turbine disc vary. In one method, the shaft is welded to the disc, which has a bolt or protrusion provided for the joint. Another method is by bolting. This method requires that the shaft have a hub that fits a machined surface on the disc face. Then, the bolts are inserted through holes in the shaft hub, and anchored in tapped holes in the disc. Of the two connection methods, bolting is more common. The turbine shaft must have some means for attachment to the compressor rotor hub. This is usually accomplished by a splint cut on the forward end of the shaft. The splint fits into a coupling device between the compressor and turbine shafts. If a coupling is not used, the splint end of the turbine shaft may fit into a splint recess in the compressor rotor hub. This splint coupling arrangement is used almost exclusively with centrifugal compressor engines. While axial compressor engines may use either of these described methods, there are various ways of attaching turbine blades. Some similar to compressor blade attachment. The most satisfactory method utilizes the fir tree design. Figure 1-64. Figure 1-64. Turbine blade with fir tree design, and lock tab method of blade retention. The blades are retained in their respective grooves by a variety of methods, the more common of which are peening, welding, lock tabs, and riveting. Figure 1-65 shows a typical turbine wheel using rivets for blade retention. Figure 1-65. Rivet method of turbine blade retention. The peening method of blade retention is used frequently in various ways. One of the most common applications of peening requires a small notch to be ground in the edge of the blade fir tree root prior to the blade installation. After the blade is inserted into the disc, the notch is filled by the disc metal, which is flowed into it by a small punch mark made in the disc adjacent to the notch. The tool used for this job is similar to a center punch. 1-49. Another method of blade retention is to construct the root of the blade so that it contains all the elements necessary for its retention. This method uses the blade root as a stop made on one end of the root so that the blade can be inserted and removed in one direction only, while on the opposite end is a tang. This tang is bent to secure the blade in the disc. Turbine blades may be either forged or cast, depending on the composition of the alloys. Most blades are precision cast and finish ground to the desired shape. Many turbine blades are cast as a single crystal, which gives the blades better strength and heat properties. Heat barrier coating, such as ceramic coating, and airflow cooling help keep the turbine blades and inlet nozzles cooler. This allows the exhaust temperature to be raised, increasing the efficiency of the engine. Figure 1-66 shows a turbine blade with air holes for cooling purposes. Figure 1-66. Turbine blade with cooling holes. Most turbines are open at the outer perimeter of the blades. However, a second type called the shrouded turbine is sometimes used. The shrouded turbine blades, in effect, form a band around the outer perimeter of the turbine wheel. This improves efficiency and vibration characteristics, and permits lighter stage weights. On the other hand, it limits turbine speed and requires more blades. Figure 1-67. Figure 1-67. Shrouded turbine blades. In turbine rotor construction, it occasionally becomes necessary to utilize turbines of more than one stage. A single turbine wheel often cannot absorb enough power from the exhaust gases to drive the components dependent on the turbine for rotative power. Thus, it is necessary to add additional turbine stages. A turbine stage consists of a row of stationary vanes or nozzles, followed by a row of rotating blades. In some models of turboprop engine, as many as 5 turbine stages have been utilized successfully. It should be remembered that, regardless of the number of wheels necessary for driving engine components, there is always a turbine nozzle preceding each wheel. As was brought out in the preceding discussion of turbine stages, the occasional use of more than one turbine wheel is warranted in cases of heavy rotational loads. It should also be pointed out that the same loads that necessitate multi-stage turbines often make it advantageous to incorporate multiple compressor rotors. In the single-stage rotor turbine, the power is developed by one turbine rotor, and all engine-driven parts are driven by this single wheel. Figure 1-68. This arrangement is used on engines, where the need for low weight and compactness predominates. This is the simplest version of the pure turbojet engine. A multi-stage turbine is shown in Figure 1-69, Figure 1-68. Single-stage rotor turbine. Figure 1-69, multi-rotor turbine. In multiple spool engines, each spool has its own set of turbine stages. Each set of turbine stages turns the compressor. 1-50. Attached to it, most turbofan engines have 2 spools. Low pressure fan shaft, a few stages of compression and the turbine to drive it, and high pressure compressor located